Okay, page 4 of applications of integration. First, we're going to do another revolution problem. Let's see. The shaded region between y equals x, which is the diagonal line, y equals 1 over x, which is the hyperbola, and x equals 2, which is the vertical line, is revolved around the x-axis. So this triangular shape is going to get spun around like so. So it's going to be kind of a, have a little hole in the middle of it right there, right? Find the coordinates of A and find the volume of revolution. Okay, I'm just going to erase this so it's a little clearer. Okay, so let's find the coordinates of A. We could do this with the calculator, or we could do it with algebra. I don't think it's going to be that hard, so we'll do it just with algebra. So we're going to take the equations y equals x, which is the diagonal line, and we're going to take y equals 1 over x, which is the hyperbola, and we're going to see when they're equal to each other by assuming that y equals x and y equals 1 over x, the y's are equal and the x's are equal. So we could say that 1 over x equals x, right? If we know that 1 over x equals x, then we know that x squared equals 1. And if we know that x squared equals 1, we know that x is equal to plus or minus 1. So in the case of A, we're talking about x equals positive 1 because this is a positive x coordinate, right? So A is going to have an x coordinate of 1, and the y coordinate would be the same. So it'll be 1, 1. So the coordinates of A are 1, 1. Find the volume of revolution. So in this case, we are going to use the formula, which we just learned in the previous page. It would be this formula here. So we're going to take the second function squared minus the first function squared, the second function being the one that is farther away from the x-axis. So first we'll take this function here, and I will put pi in front, right? And the limits of integration are going to be the x-coordinate of A and 2, so it would be 1 to 2. And the first function squared is going to be the function that's farther away from the x-axis, which is y equals x, so it would be x squared. The second function squared would be the inside function, which would be 1 over x, so it would be 1 over x squared, and dx. And so first thing we're going to do is we're going to take the integral of x squared, which is just x cubed over 3. And then we're going to look at the second function. I'm going to rewrite the second function. Instead of 1 over x quantity squared, I'm going to put 1 squared, which is just 1, over x squared. And this is the same thing as x to the negative 2. So the integral of x to the negative 2 would be x to the negative 1, right? Because negative 2 plus 1, and then I'm going to divide by negative 1 also. Okay, and oh, I already took the derivative, so I don't need to write dx here. This is actually the derivative, or the integral already. And now I'm going to, and I'm going to use the limits of integration now to find the definite integral. So now it's going to be evaluated from 2 to 1. And don't forget that everything should be multiplied times pi. So let me put the pi in there also. Okay. All right, now let's simplify this by making both of these plus, okay? So basically that's an easier expression now. X cubed divided by 3 plus x to the negative 1. I'm just going to get rid of those. All right, and so now I'm going to plug in 2 in for the x, and I'll get pi, and I'll have 2 cubed, which is 8 thirds, plus x to the negative 1 with 2 plugged in would be 1/2. And then I'm going to do the same thing with 1. So I'm going to put 1 in for x cubed to be 1/3 plus 1 over 1, which is 1. And let's see. Put pi on the outside. 8 thirds minus 1/3 is 7 thirds. 1/2 minus 1 is negative 1/2. So 7 thirds minus 1/2, that's the same thing as 14/6 minus 3/6, that's equal to 11/6 pi. Okay? I don't like the way I made that fraction. 11/6 pi. Okay, let's do number 5. The shaded region is revolved around the x-axis. State the coordinates of A, and find the volume of revolution. Okay, so we're going to find this point first. Again, this is not going to be too challenging, so we'll just do it without the calculator. So we're going to find the intersection between this function and this function. The way we do that is we set the y's equal to each other. So it would be square root of x minus 4 equals 1. Square both sides, we get x minus 4 equals 1. X equals 1 plus 4, which is equal to 5. Let's see. That makes sense. This looks like x equals 5, right? And then to find out what y is, we plug it into either equation. Well, actually, this equation, y equals 1, says that y is always equal to 1. So our coordinate for A would be 5, 1. Find the volume of revolution. Okay, so now we're going to use the point A for our first limit of integration. 5 is the leftmost x value. The rightmost x value is 8. And we would do the parabola, which is, or it's a sideways parabola, which would be square root of x minus 4 squared minus, the inside function is y equals 1, 1, and, oh, I'm sorry, messing up the formula here. Remember, you got to put a pi here, first of all. Then you're going to have the outside function squared, and then you're going to have the inside function squared. The inside function is simply y equals 1, so it would be 1 squared, and then dx, okay? And so let's do this integral here. So, you know, the way this would look, if you're wondering, is, again, kind of like a donut. So this would be the outside ring. This would be the inside hollow ring. And then this hollow ring would go all the way over to there. So it would look kind of like, I don't know, a little round half ball with a hole drilled through it or something. So let's take the integral of square root of x minus 4 squared. Square root of x minus 4 squared is the same thing as x minus 4 with no square root or squared. So if I take the integral, that's pretty easy. It's x squared divided by 2 for the first term, minus 4x for the second term, then minus 1. If I take the integral of minus 1, it would be minus 1x. And then the limits integration would be 5 and 8. I'm going to simplify the inside. It'll be x squared divided by 2 minus 5x. And then that's integrated between 5 and 8. And then I'm going to plug in 8 in for the x's here, so it would be pi times 8 squared, which is 64, divided by 2, minus 5 times 8, which is 40, minus, and then I'm going to put the 5 into the x here, so it would be 5 squared is 25 halves, minus 20, no, not 25, yeah, 25, because 5 times 5 is 25. So let me simplify this. So it would be pi times, and 64 divided by 2 is 32, minus 40, and then minus 25 halves, which is minus 12.5, plus 25. Okay, and so let's see. I'm going to use the offline calculator here to do this simple addition. 32 minus 40 is negative 8, minus 12.5 is negative 20.5, plus 25, that's 4.5, so we end up with 4.5 pi. Okay, second to last problem, number 7. A chord of the circle with the equation x squared plus y squared equals r squared, remember that's the equation of a circle with radius r, is parallel to the y-axis and has length equal to the radius of the circle. A solid of revolution is generated by revolving the minor segment cut off by the chord through 360 degrees around the y-axis. So let's try to draw this picture. X squared plus y squared equals r squared is a circle centered at the origin. So basically it looks like that. The radius of the circle, of course, is r. And they said that they're going to cut a chord parallel to the y-axis with a length equal to the radius. That's the radius, right? So if I cut a chord with a length equal to the radius, it would be about there. Okay, so there's a chord. Minor chord means they're talking about this part here as opposed to the rest of the circle, which would be the major chord. Okay? Now what they're going to do is they're going to figure out what would be the volume of the solid generated by revolving it around the y-axis. So that would look kind of like this. So it would be kind of like that wedding ring picture that we made last time. It would be a sphere with a a cylinder cut out of the middle. And so the key here is we need to figure out what these points are so we could do the limits of integration. Let's see. The equation we have is x squared plus y squared equals r squared. We are going to do an integral with respect to y because we're revolving it around the y-axis. So here we do want an expression with just y's in it, an x equals blah 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 y equation, which we can find by subtracting y squared to the other side and then taking the square root. So it would be x equals the square root of r squared minus y squared, and that's what's going to go for one of our formulas. It would be that one, the outside formula, right? So, oh, and the other thing that we haven't done yet is we need to figure out these points, the coordinates of the two arrows here. So the way we're going to do that is we're going to figure out, let's see, I'm going to draw in a different color. Like basically what we define here is this is a triangle, and this length here is r divided by 2 because the length of the line which forms the chord is r, right? And it turns out that this is also r because the distance from the center of the circle to the edge of the circle is r. And so I think that we formed here is a 30, 60, 90 triangle, right? Because if this is r and this is a half r, then it is a 30, 60, 90 triangle. And then we automatically know that this length here is going to be square root of 3 over 2r. Okay, so does that help us figure out the limits of integration? Actually, just by knowing r over 2, I think we already kind of knew it, so not a big deal. Okay, so like, for example, this point here would be positive r divided by 2, comma, I'm sorry, it would be square root of 3 over 2r, comma, r divided by 2, right? And then this point here at the bottom would be square root of 3 over 2r, comma, negative r divided by 2. Okay, so we have 2 points defined, and the coordinates that we would use for the limits of integration would be the y coordinates, right? Because everything is in terms of y for this integral. And let me just give myself a little bit more space. It's going to be pi, and the limits of integration are going to be 2 y coordinates, so it would be minus r divided by 2 to r over 2. The inside here is going to be x equals blah 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 r, which we found out is square root of r squared minus y squared, and we are going to take the square of that. But just before, we'll go ahead and write the square root function just so you can see that, right? So we're going to put the x function there, and then we're going to square that, and then we're going to subtract the inside function. The inside function is basically x equals square root of 3 over 2r. So we'll put square root of 3 over 2r, and that'll be squared also, and that'll have a dx after it, and then now we can start simplifying and taking the integral. So first simplifying, I'm not going to write the limits of integration because we can already see that. When we square the square root, we'll just get r squared minus y squared. When we square square root of 3 over 2r, we'll get a nicer looking expression. It'll be 3/4 r squared. And now we'll take the integral and we'll get, remember r squared is just a number. We just don't know what r is, right? I think. Yeah, we don't know what r is. So the integral of r squared is not r cubed over 3 because r is not a variable. The variable in this case is I'm sorry, it's y, not x. Oopsie. Everything is in terms of y, right? So it would be r squared y, and then the integral of y squared would be y cubed over 3, and then the integral of negative 3/4 r squared. Remember, r is just a number, it's not a variable. So when I take the integral of this, I just add a y to it. And then I've taken the integral of everything, so why did I write the integral there? I wasn't supposed to. Okay, and then I'm going to put the limits of integration here finally, just the same thing I put before, negative r divided by 2 to positive r divided by 2. And now I'm going to substitute in the r over 2 and the negative r over 2 in for the y's. So it'll be r squared times y, which is r over 2, which should be r cubed over 2 minus y cubed would be r cubed over 8. R cubed over 8. That's 3. Minus 3/4 r squared. Oops. R squared times r over 2, so it'd be r cubed over 2. And then I'm going to subtract negative r over 2 substituted in there. So it'll be negative r over 2 substituted in here would give me negative r cubed over 2. Negative r cubed over 2. And then negative r over 2 substituted in here would be minus negative r cubed divided by 6. No, divided by 8 times 3. So it would be plus r cubed divided by 8 times 3, which is 24. And then the last one I would have minus 3/4 and then negative r over 2 for y and times r squared. So it would be negative r cubed divided by 2. So 3/4 times negative r cubed over 2. Negative r cubed over 2. And I think we're almost done. Okay. So now I'm going to put pi on the outside. I'm going to try to combine like the fractions with similar denominators. So here I have r cubed divided by 2 plus r cubed divided by 2 because there's two negative signs here, right? So that would just be r cubed, right? Now let's look at the next. So this one would be minus r cubed divided by 24, and this would also be minus r cubed divided by 24. So that would be a total of minus r cubed divided by 12. And then the next one would be negative 3 over 8 r cubed, and this would be negative 3 over 8 r cubed also. So it would be negative 3/4 r cubed. So now I'm going to combine the r cubed. So I have r cubed minus 3/4 r cubed. That would be 1/4 r cubed. And then, minus r cubed divided by 12. So that would be 3/12 minus 1/12. So it would be 2/12. So it would be r cubed divided by 6. So the volume here is given to be pi r cubed over 6, and that's exactly what I got, right? So perfect. So let's go down to number 9, which is a kind of a paradox. Prove that the shaded area from x equals 1 to infinity, this area here, is infinite, whereas its volume of revolution is finite. Okay, so the volume contained by this revolution is finite, but the area in this diagram is infinite. Pretty weird, huh? So let's just do this as two separate problems. We're going to show the volume of revolution as a certain number, and then we're going to do the integral of this area here, and we're going to find out that it's infinite. Okay, so let's do the revolution first. First of all, we have this is not a difficult revolution. It's easier than the other. So it's y equals 1 over x is the function. We're going to do it in terms of y. The limits of integration are pretty easy because one side starts at 1 and the other one goes to infinity. And then inside we're going to have the function 1 over x. Except we got to have it in terms of, oh no, we're going to do it in terms of x because we're revolving around the x-axis. So actually it's not dy, it's dx here, right? And then we're going to square it because it's pi r squared, and we're going to put pi in front, okay? And then for this one over here, the area, we're going to do something similar, except it's going to be 1 to infinity and just simply the area, okay? And I can already see why one of them is not infinity and the other one is. Interesting. Okay, so the one on the left, which looks like a little trumpet or something, we are going to simplify it by squaring both the top and the bottom. So we'll have 1 over x squared, the integral of that, and the integral of x to the negative 2 is x to the negative 1 divided by negative 1, which is negative blah, blah, blah. And then we're going to have the limits of integration, which are infinity and 1. And the mathematically correct way of doing this is we say the limit as b goes to infinity of pi negative x to the negative 1 of b of 1 to b. So we use a limit to, instead of just plugging infinite in there directly, so that the math is as simple as possible. And just at the very end, we're going to put infinity in as a limit, and then it becomes a limit problem. So we're going to have pi and then negative b negative 1 minus pi, and then we're going to have negative 1, negative 1 to the negative 1. 1 to the negative 1 is just 1, so it's negative 1. So our answer is pi, negative pi, b to the negative 1, plus pi. And if you look at this, infinity to the negative 1 is 1 over infinity. Basically, that's 0. Okay, so when we do take the limit, sorry, this actually had a limit, right? Equals the limit of b goes to infinity. And here we actually put something in for b, which is infinity, and then we find out that the first term is 0 and the last term is just pi. So it turns out the volume enclosed by this trumpet is pi. Okay? Then we're going to go do the other problem. And when we take the integral of 1 over x, so instead of doing that integral, when you do learn how to do improper integrals in the green book, they're going to tell you to do this, but you could just do it like that. I mean, no biggie. Okay, and then so we got the integral of 1 over x, which is x to the negative 1. When we take the integral of x to the negative 1, we get natural log of x, right? And now you can kind of see why one of them converges and the other one doesn't. When I say converge, it means one of them becomes just a finite number, and the other one becomes infinity. So this is still a limit, right? And now I'm going to plug in the b, so I get natural log of b minus the natural log of 1. Natural log of 1 is just 0, right? Because the any base log of 1 is always 0. And so basically the answer is natural log of b and then we put infinity in for b, and then the natural log of infinity is just infinity. So does not converge. So this, yes, the volume is indeed infinity. We just confirmed that. So little hard, it's easy to see why the integrals, one converges, the other one doesn't, right? It turns out that anything that's like a higher order than 1 over x squared also converges. 1 over x does not converge. So the magic number of this power here must be at least 2 for the integral to converge. So that's the end.